Okay, so let's begin. We will be discussing today quantum gravity coupled to conformal field theory. Before I start this new subject, let's put in a nutshell what we actually know. Actually, it's always useful to kind of remember where this or that formula comes from. It's practically impossible actually to use effectively some formula if you don't know their origin. Anyway, so we had the following facts. Holomorphic T of Z, energy momentum tensor. We have word identity. We have primary operators. Which transform through themselves. That's the definition, basically, of the primaries, that they, when you perform holomorphic transformation of Z, the primaries transform through themselves. That's while the secondaries transform through themselves and the primary. That's the difference. We see that we have the general, so the VI word identity implies it implies the presence of secondary, of many types of secondary operators. What else? Some combination of the secondary operators form null vectors. We have operators of which we have degenerate primaries. Primaries, we call it psi rs, with two integers, which are secondary of which turn to zero at the level rs. And we have a differential equation from RPE implies differential equations for psi-rs. And from differential equation we actually derive OPE. Here we have operator product like tip C, and here we have psi-psi. We saw that it is possible to have the minimal models. Which are defined as consistent field theory, satisfying all these conditions, having all these features, better to say. And the minimal models, they have finite number of primaries. We can also, what else can we say? We will take all that and we will see how these features are modified in the presence of gravity. Well, the other thing is that we can look at the correlation function. The other thing is conformal blocks, which exist for each primary, and which is simply the contribution of we take some primary operator plus all secondaries and find the amplitude, find the 4-point function, which looks like that. We have any operator, or in this case I have psi, 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 and here we have an operator O, and all possible secondaries of this operator. And we get something which, when we have only one operator, it doesn't satisfy yet the conformal bootstrap condition. Is basically associativity of the operator product expansion. And it is just the relation that sum of this guy is equal to sum of that guy. Basically, while in the minimal models, one operator would not satisfy, the conformal block does not satisfy this, but the sum over several, for example, in the Ising model, we have only 3 primary operators, and they satisfy this relation. 3 primaries, and of course, infinite number of secondaries. This is the conformal blocks, the contribution of all these things is completely computable due to word identities, because we know, when we know the contribution of the primary operator, you easily you can easily find the all possible contributions of the secondary operators. So conformal blocks can be actually, it is a well-defined function which can be calculated perturbatively, step by step. Perturbatively in the sense you take, say, small distance between these 2 points, and then you expand it in terms of the distance, and all the coefficients, all the Taylor coefficients are calculable from the word identity. So this is basically what I said is the structure. And by the way, excuse me, forgot to finish this. By the way, we will perhaps encounter with conformal blocks in the completely different situation. Actually, in recent work shows that they are related in a rather strange way to instantons, which we definitely will be discussing. But at the moment, that's not what interests us. But what interests us is what happens to all that. This is a pretty general construction. What happens to all that if you couple it to gravity? And that will be our main topic today. Before I go further, it's also, I don't want to say, don't get me wrong, that the minimal models are the only possible quantum field theories. In the first place, there could be also minimal models, but for more extended algebra. Here, there are minimal models. What do I mean by that? Here we have only one algebra, which is the Virasoro algebra, or algebra of conformal deformations. But in many cases, there are also conserved holomorphic current, not only holomorphic 10 energy momentum tensor. So there are models in which you have T of Z, of course, and also you have a holomorphic current, one of many. Or you can also have the thing we discussed last time was, well, we can also have an anti-commuting spin 3/2 current, which means supersymmetry. That's, I remind you, what happens in 4-5 minimal model. But returning to this, if you have this situation, you can generate secondaries not only by applying energy momentum tensor, but also by applying current. And so if you can have minimal models with respect, so you have primaries with respect both to T of Z and J of Z, and the secondaries. But if you take this thing and look at it as a concentrate only on the T of Z part, there will be you will have the impression that there is infinitely many. That's not the impression, that's correct conclusion. There are infinite number of primaries with respect to T only, but only finite number of primaries with respect to T and J. So that's, I will not, we will, well, one of the simplest examples is what you had in your homework, namely the tearing model. In the tearing model, you have the U1 current, and you, of course, have a holomorphic energy momentum tensor. And correspondingly, you can, well, and this is a minimal model, but with respect to both. Okay. So it's good to have it in front of you. Now, when we discuss coupling it to gravity, let's first remember in general what we mean by coupling things to gauge fields or to gravity. When we have quantum electrodynamics, we start with correlation functions like that, or we start, excuse me, with Lagrangian for free fermions, say the Dirac Lagrangian. They could be massive, for example. These are free fermions, and then this is the zero order Lagrangian, and then we add the interaction term, the current, electromagnetic current, multiplied by the gauge field. We introduce it to the appearance of gauge field it's automatic if you postulate gauge invariance. Then this for constant alpha, this is of course invariant, but when alpha is not constant, you will have to differentiate it. When substituting, it will not be a symmetry, of course, and it should be compensated by this term, and it is. It's of course very elementary what I'm saying, and you have to look at the gauge transformations. Anything physical should be invariant under these gauge transformations. And we add the Lagrangian for electromagnetic field itself. And as we already discussed, actually this combination is needed to to have gauge invariance. This is I just remind you some elementary facts. Now, one more elementary fact is that you can always, the partition function in QED, I'm still talking about QED as the most familiar example of field theory. You generally have dA, you have this action f mu nu square, f mu nu is this guy. And we can actually add e to the minus w of a, where e to the minus w of a is defined as integral over fermions of this Dirac-Lagrangian. So diagrammatically, it means that W of A is just the fermionic loop in the external field. And so the strategy for adding gauge fields is you first find effective action for these gauge fields. And well, which is non-local, you find it by integrating out fermions. And that this W of A basically gives the vacuum permeability and dielectric constant and so on. In particular, an important object is the polarization operator. If we start expanding in A, it is the correlation function of two J's. And it must have the form f of q square delta mu nu minus q mu nu. And if we have no singularities, this form, or sometimes I can also write it down, q square delta mu nu perpendicular multiplied by f of q square. It's a convenient notation. This delta mu nu perpendicular is a delta mu nu minus q nu divided by q square. Okay. This, if we say that we have only massive particles in the theory, we believe that there will be no singularities. All singularities of green functions, of amplitudes, are related to the mass. They are generally, if all momenta is much smaller, q square less than all masses, that means that particle cannot be produced, and we have analytic pi mu nu is analytic for q square negative or small enough. That means that f tends to a constant, and that means that we have this formula. By the way, it's another way of writing this, which we will need. If you multiply it by a mu a nu, then what kind of and integrate over q, that is simply f mu nu square. So this is just the way to write down the electromagnetic Lagrangian. And now we generalize it to gravity. Actually, we could find the Lagrangian, this form of Lagrangian, by saying that we need this symmetry, which is a mu to a mu plus q mu alpha. So if we write down general polarization operator pi mu nu q, then it must satisfy this is one of the, which is just current conservation, as you see. So that should be familiar. Now maybe a little less familiar things. How this generalizes to gravity. How using in this language, what would be the, let's start with the Einstein action. What would be this, in these notations, the kinetic energy and so on. What would be vacuum polarization? By the way, you see from here that we have dielectric, that this term generates the dielectric constant. How would you say? How would you argue that? That the value, actually I'm claiming that is that the value f of 0 is related to the dielectric constant. Why? Yes.
Well, if you write down, say, the energy of the magnetic,
Yes.
of the electric field, it's E squared over.
Yes.
Yeah, well, E squared times epsilon.
Correct.
Would precisely correspond to f of 0 times.
Yes, you are quite right. Another way, absolutely correct, yes. But also another way is simply to notice that the effective action, the action, where was the effective action? Oh yeah, here. The effective action would be 1 over E square, this is a bare charge, plus f of 0. And that's what will be multiplied. This thing is just trivially related to dielectric constant. If you do with magnetic permeability, it's the same story, but in relativistic case, contrary to, we will be in a lecture or two, we'll be discussing non-relativistic case in which you have several functions. In relativistic case, as we discussed, because speed of light is 1, mu, the magnetic permeability, is 1 over epsilon. Anyway, that's all well-known stuff. Now let's talk about gravity. Let's talk about gravity. In gravity, we have basically the same thing, the same structure, except that we have the metric tensor, which we can decompose onto delta mu nu plus h mu nu. And if we consider weak gravitational fields, at first we will need generic gravitational field, but like in black hole and so on. But let's consider first perturbatively, things perturbatively. Then the coordinate invariance of g mu nu simply means that we must have symmetry q mu epsilon nu plus q nu epsilon nu. So that's the analog of gauge symmetry. And of course there will be some transformation law for bosons and fermions, which we will discuss. But let's first begin with polarization operator or the Lagrangian. Let's begin with the Lagrangian with the Einstein Lagrangian, which is the standard Einstein Lagrangian is that it is proportional to this guy. But it will be convenient for us to write it down perturbatively. And that we can figure out how it looks without really, it's a bit messy, as you know. Scalar curvature in general dimension is a somewhat complicated object, but we don't need all this. We can actually reproduce it in a very simple way. We simply have to write down the expression and that's our effective action. So we have this expression. Now we have to find this guy. And this guy is actually should have this invariance. So we have, using our building blocks, which we use there, give me some example which would be fine, which would actually satisfy this gauge symmetry. You have a nice tensor in your disposal, so you can use it, can try to use it.
Some combination and
yes. So for instance, we can try for this guy. Something like, we can take C, delta mu C of Q square, delta mu lambda, perpendicular delta nu gamma. Let's take some A of Q square, delta nu gamma, perpendicular, plus B, delta mu nu, perpendicular, delta lambda gamma, perpendicular, plus symmetric part. We have to interchange mu and nu. And the strange thing is that it's not the answer. It's clearly not the right answer yet, because we have two arbitrary functions. What can we say? How these functions in the low energy limit behave as Q square goes to 0? So this is not the answer. Also, excuse me, I have to finish the phrase. What I meant is that in Einstein action, we have only one term, while here we appears to have two terms. So something goes clearly wrong here. It is not the final answer, but it is a step towards correct answer. So first of all, how A and B depends on Q?
S2 goes to 0.
Yes. To compare it with Einstein or with QED. Suppose we want yes.
do the Newton constant.
Yeah, Newton constant, of course. Well, but if you have remember this in QED, P mu nu was Q square delta mu nu perpendicular. Why it was like that? How we argued it must be like that. But why? Why not simply delta mu nu perpendicular? This is something we just discussed. So why why we need extra factor of Q? Without, by the way, without this extra, well, okay, think a little bit. there is an extra q square in front.
It's clear from action.
It comes from the action f mu square, but why it must be present also in the vacuum polarization term. We have the bare action, which we wrote down f mu square, but then we say that in W, this polarization action, which this W in quadratic approximation, we expand it up to a square, it must also contain only this q. It will never, in this theory, it will never have the term without q square.
I think we shouldn't have terms like q nu over q squared, because they would trigger like long range order, like it's superconductivity.
You are basically right, yes. What happens is that when we calculate this thing, this diagram, as I mentioned, doesn't have a singularity, non-singular at q equals 0, if masses are not 0. If masses are 0, there is some weak singularity, but it doesn't change the conclusion. So, and we want this to be equal to be proportional to, if we just take delta mu nu perpendicular, we are in trouble because it contradicts this condition. Delta mu nu perpendicular contains the pole. And this pole cannot come from this diagram because the diagram is analytic. You just write down Feynman rules and find it analytic. In fact, where, by the way, this diagram has a singularity in q square. What's the position of the singularity?
M. Correspond to the production of the pair.
Yes. What you are saying is quite right. So, if we take, okay, so, and then finish it.
4m squared. Right?
4m square, indeed. If we take, for example, pure energy, Q0, Q equal to 0, then the minimal energy needed for producing this pair is 2m. So Q square is 4m square. And you have a so-called threshold singularity at this point. In any case, that's just a side remark. In any case, that explains, in order to compensate in QED the singularity of this projection operator. It's a projection operator, obviously. By the way, why it is a projection operator?
With respect to Q?
Yes, with respect to just anything. What it does when, suppose you multiply it by some vector, and you obtain another vector. So what is about this other vector?
It's perpendicular.
It will be perpendicular to Q, so which means that the square of this tensor is again the same tensor. Okay, all these are side remarks. We're returning here, and by the way, the thing is that we have Q square, and it's the minimal possible power. So the result is, strictly speaking, you have some complicated function of Q square multiplied by delta mu nu perpendicular. But then you take Q to 0 and you keep the minimal power of Q, which is a minimal number of derivative. And that's precisely F mu nu square, the Maxwell action. Okay? So that's the way to understand the Maxwell action. Now let's do the same thing with gravity. And we know that basically some hint is that the Maxwell action is actually, the Maxwell equations are for the potential are second order corresponding to this q square, which we have. In equation for graviton is also the second order. After all, they just should, in non-relativistic case, they reduce to the Poisson equation. So we have two terms here, and I want you to think a little bit about it. So let me. What if we take what is the minimal power of Q which we can have, and so on. So let me So once again we have something like that. Same argument. There is no singularity should be no singularity at q equals 0, and we have, if we multiply it by h mu nu h lambda gamma, we can have two terms. I rename it C1 delta mu lambda delta nu gamma perpendicular plus C2 delta mu nu delta lambda gamma perpendicular h mu nu h lambda gamma. Okay, and if we think, so generally these are functional of, we have C1 of q square and C2 of q square, analog of dielectric constants and so on. So what can you say about the limit q to 0?
Why we cannot have the other term, let's say?
What?
Why we cannot have mu nu and lambda?
Why there was a symmetrization, or what?
Yeah, yeah.
Why don't I symmetrize? Not needed here because you can, but not needed because you multiply it by symmetric h mu nu and h lambda gamma. So it's actually I multiplied precisely to avoid extra writing here. Okay, but now I want you to decide what are these functions at q equals 0. Okay, q square, but then it seems that we have a more general Lagrangian than the Einstein, and it's pretty dangerous to fight with Einstein.
We should ensure like 1 over q to the 4 acceleration.
Right. The problem is you can have q square,
Yeah,
but then you have q mu, q lambda, q nu, q gamma divided by q to the 4th, and it is still a non-local term. When I say non-local, by the way, all these terms are not, these singular terms in coordinate space correspond to non-locality. It's not the local Einstein action or local Maxwell action, but just some double integral over x and x prime. Okay, so what's the way out?
C1 equals minus.
Yeah, right, and that's precisely the Einstein action, actually. That you can check by comparing with Einstein action, consider it as a home exercise. So indeed, we get C of q square delta mu lambda delta nu gamma minus delta mu nu delta lambda gamma multiplied by h mu nu h lambda gamma and that's our action. This time everything is fine. If C is Q square, then this is the local Lagrangian, because no singularities at Q equals 0. You could say, okay, but why I can leave it different or drop, say, I can set C2 equals 0, and I can take C1 to be Q to the 4th. In this way, I will compensate for this. So what do you think will be wrong with it? It has actually a certain attraction, because, as you know, Einstein theory is non-renormalizable, and it looks nice. It's because you have quadratic divergences in Feynman diagrams. If you take if you put Q to the 4th here, the divergences will be logarithmic and things will resemble quantum electrodynamics and so on. So but there is some problem here. Why it is not possible to cure the divergence problem simply by taking higher derivative, higher Q, higher power of Q.
Won't have the classical limit.
That's true, but to some extent that's true. But in fact, the main reason is this: if you have when we have a propagator, then the residue, suppose we have omega square minus p square minus m square, propagator for this particle. The residue at the pole is the norm of this state. It's in quantum field theory, it's interpreted as a norm. The residue in the Green function is the probability for having this particle. Now, if you have the fourth power here, it actually decomposes into two such terms, but one comes with a negative sign. You need, at large omega, you need to cancel 1 over omega square term.
It will violate unitarity?
Huh?
It will violate unitarity.
Yeah, it will violate. The result is that if you have a propagator which behaves like 1 over omega to the 4th, I don't want to spend too much time on it, but we'll be glad to discuss it later. So if it's 1 over omega to the 4th, then necessarily there will be a negative norm state. There is, for the most general propagator, just I'll give you the hint where it comes from, there is the so-called Lemon representation, when you represent Green function as rho of m square, or q square minus m square plus I0. That's the general representation for the in-field theory. The Lemon representation. And the function rho measures the probability for having the given state, so it must be positive. But if it is positive, you see, as q goes to infinity, the result should go down as 1 over q square. It goes as q goes to infinity. And so because of that, 1 over q to the 4th can appear only if rho is non-positive. That's from the point of view of geometric Einstein-like expression, this idea of setting here q to the fourth means that you take the action which is not simply the scalar curvature, but scalar curvature square or some Ricci tensor square and so on. But again, that's a convenient way to study it. Still, sometimes it is very useful to have higher derivative gravity and then reduce it by some extra constraint to the ordinary gravity. But we will not be discussing this. I just wanted to explain to you what we really, how the gravitational analogy with the gauge field when you construct gravitational action. Okay, all this is good, except one. Now let's go back to our main problem, which is quantizing two-dimensional conformal field theory, adding gravity to two-dimensional conformal field theory. And we immediately encounter the problem. When we look at this expression in two dimensions, I claim that, and I will ask you to justify this claim, my claim is that in two dimensions this tensor is zero, this difference is zero, and find some simple argument why it is so in 2D, remembering what's the meaning of this delta symbol is and so on. Or I can recommend you.
No
It's perpendicular to two. How
To what?
No.
Well, but think like that. Is what is perpendicular? Think geometrically here, or think of, for example, direct q along the axis 1. That will simplify things. And then what happens to this guy? Well, what happens is that there is only one component. If it is perpendicular to the axis 1, there is only one non-zero component, which is delta 2, 2. So, for instance, if you take here delta 1, 1, it will be 1 minus q1 square divided by q1 square, so it will be 0. Okay, delta 2, 2 will not be 0, it will be equal to 1. But now substitute delta 2, 2. These terms are identical. It's just they have the only non-zero component are when all the component equal to direction to the number 2, and then it vanishes. So we don't have the Einstein action in two dimensions. And more general geometric way of saying the same thing is to notice that if you write down, of course you can write down formally the Einstein function in two dimensions. This argument tells us that it's something should be wrong. It's the integral of the total derivative, and it's actually related to topology, not to geometry of the surface. It's proportional to Euler character of the manifold M, which we will discuss a little later. So, and that's So this is topological invariant. While in 4 dimensions there is also Euler character, and it is also expressed in terms of curvature, but it's quadratic in curvature. There are actually two invariants, two topological invariants in 4 dimensions. There's Euler character, and another is called Panchagin class. It's just they both are some quadratic combination of the curvature tensor. And you see all that when you expand in the weak field limit. You can see all that simply by noticing that things disappear in the weak field limit. All right. So now let's think a little more, and we will see that there's some strange paradoxes. By the way, before I go into this, it's a few words about the motivation of this thing. First of all, it's most importantly, it's an interesting theoretical laboratory. What gravity does to theory. In 2 dimensions, we can hope, and this hope is justified, that we will find exact solution of the gravity coupled to conformal to CFT. There is an exact solution. We will find it, and it will teach us a lot of lessons about what is observable, what is not in gravity. While in higher dimensions, so far we can only do some mostly perturbative things. Then there is a second reason why it is interesting. Actually, string theory, which describes, among other things, it describes gravity in 4 dimensions and in any dimensions. This string theory is nothing but 2-dimensional CFT coupled to gravity. So if we learning, that's sufficient motivations to study these things. And one very surprising thing which will come out is that those minimal models, they become much simpler when you couple them to gravity. Usually we used to think that coupling to gravity is very complicated, but here it simplifies the theory. All right, enough words about it. We will start with some strange feature, some small paradox of the type we discussed. Let's consider a free massless field coupled to gravity in 2 dimensions. We have square root of g alpha beta, d alpha phi, d beta phi. Or we can consider just as well free fermions, some particles coupled, massless particles, conformal and coupled to gravity. It's clear that this thing is actually classically conformal, because if you take G alpha beta equal to rho delta alpha beta, you see that this term will be equal to rho, this term will be equal to rho minus 1, and we come to the strange conclusion that gravity doesn't couple to this field phi. In fact, the conclusion is incorrect. We will see in a moment that it is incorrect. And it is incorrect, and I probably didn't formulate it in enough detail. There is one missing link in the logic. So for such metrics, indeed, this coupling disappears from the action. But you can say maybe for other metrics it will not disappear, and that's indeed what will happen. But the point is, the paradox is that any metric by the choice of coordinates in 2 dimensions can be reduced to this form. Namely, more precisely, you can always find the gauge transformation such that the metric after the gauge transformation becomes conformally Euclidean. This is called conformally Euclidean. Now, give me some naive counting which shows that it will not be the proof, but kind of an intuitive explanation why in 2 dimensions it's always possible.
So you have 3 independent parameters?
Yes. Yes, that's basically the point, yes. You have function rho, and you have 2 functions f. And you have precisely 3 components of the metric tensor, because it's symmetric. And so it's not surprising that in this case you can do this. You can always choose this gauge. In 3 dimensions, for example, it would not be possible. In 3 dimensions, you will have 6 components of G and only four unknown functions, arbitrary functions. So it is specifics of 2D, and the naive conclusion, which we will contradict immediately, is that gravity doesn't couple to this field. Okay, but now let's change the gauge once again. Here we worked with the gauge rho of x, rho of xi, say xi plus and xi minus, d xi plus, d xi minus. That's a light conversion of this thing. By changing coordinates, you can, of course, go to another gauge. And the gauge which turns out to be very convenient is the so-called the light cone gauge. Namely, we can, by changing coordinates, and that will be a homework. That's very easy to change these coordinates. You can transform this metric into another one, dxi plus dxi minus plus h plus plus dxi plus square. The reason why it is convenient will be clear immediately. It's again not surprising from the point of view we had one function rho here, one function h here, so it's the same counting which tells you that things are okay with changing variables. What we're doing, okay. Well, if we now rewrite, so before this thing disappeared, if we now rewrite the action in this gauge, we obtain the action of the following type: integral d to xi. Notice that the determinant, that's by the way important, the determinant of the metric, it's rho here, and it's equal to 1 here. So the action is simply d plus phi, d minus phi, plus h plus plus, d minus phi square. What is the physical meaning of this operator, d minus phi square, which couples to h plus plus? What would you expect? This is yes?
Energy tensor for this.
It's energy, it's precise, it's energy momentum tensor. So we have the energy momentum tensor for the massless scalar field is just d minus phi square. Maybe 1/2 here. It's all very nice. H plus plus appeared explicitly. Now, the statement now is that it cannot gravity does not decouple. You can say, okay, but let's calculate some object and it may still decouple. And now I want you to make the we now take the induced or effective action, and this induced or effective action is
So you mean classically it decouples, right?
Classically it does not, but because h plus plus explicitly here. From this action, yes, it decouples in this gauge, but it becomes of this form in this gauge. The action changes, you see, because we change coordinates. By itself, it's nothing. There's no paradox here. In different coordinates, it will look differently. The question is whether, when you start calculating, whether you get different results for some green function or for some matrix element, for some invariant thing. You cannot compare directly the two coordinate systems.
Classically, we'll get the same equations. But classically, for this, we'll get the same equations of motion.
Yes, actually, you will get the equation. Well, okay, let me explain this. What you are asking is important to understand. Let's simply write down this class. I want to go directly to quantum, but let's spend a minute on the classical. When you vary this action, since rho disappears from this, you will get the Laplace equation or wave equation of this form in gauge C. It's a C gauge, and we will get the equation of the following type: d plus minus h plus plus d minus phi is equal to 0 in the second gauge. And there is no, so far, there's no paradox at all, because you simply say it's just change of variable in this equation. This is in variables we're using here and here are different. They are related by some transformation. So it's not surprising that the equations are different.
No, I mean, it seems that the equation is like in a
that's right.
Space, right?
The what?
The first equation like in a split space.
Yes, exactly. The second equation can be transformed to the flat space by coordinate transformation. So, so far nothing happened. You see, it does have to look. It's just that if you calculate something invariant under coordinate transformation, you will get the same result. Okay, but now I'm coming to something interesting. Namely, let's calculate the second order term in two different gauges. Well, here is in the light cone gauge. So this is light cone gauge. Well, we know from it's the correlation function of two energy momentum tensor. So it's precisely like in quantum electrodynamics, fluctuations of the in the vacuum create polarization operator. So in QED, by the way, is it possible for you to see this? Okay, or I can avoid writing here. Okay, so in QED we have this thing, fluctuation of current create polarization. Here, fluctuation of energy momentum tensor create polarization. And this is in the light cone gauge. While if we try to calculate it in the conformal gauge, there is nothing to calculate, and it seems that we get 0. So we would conclude naively and incorrectly that this should be 0. But what it contradicts to? We discussed once already the feature of energy momentum tensor.
It's always non-negative.
It's non-negative. It's equal to central charge, actually. Remember when we discussed the Virasoro algebra, we claimed that the central it must contain the central extension. The energy momentum tensors are non-negative, otherwise we break down positivity, which actually happens sometimes. There are theories without unitarity which are very useful, but not in this case. Okay, so let's calculate and then try to understand what has happened. The calculation is extremely easy. First, it is proportional to what is called a central charge, which is equals to 1 for the free field, multiplied, if it is at the point x, if it is at the point 0, then what would be the answer? How it depends on x? Yes, correct. So we have 1 over x minus to the 4th power, which follows from dimensional and from the Lorentz symmetry. Lorentz symmetry tells it that it should be the 4th power of the x minus in the denominator, and scaling is also satisfied. You usually have to use two, as you will see in a moment, you have to use two things. And since in order to find the correlation function of H++, we will have to invert this thing. Let's go to the momentum space, to the Q space. This is X space. This is Q space. So we have to calculate integral d2x divided by x minus to the 4th e to the iqx. And actually, if we don't care for the overall normalization, which can be restored after you get the answer, you should be able just to read the answer from here. Using the Lorentz and the scaling.
Should go like q squared.
Yeah. It should go. It should contain the scaling. Should be x squared divided by x to the fourth. So it's 1 over x squared, and as you said, it should scale like q squared. But q squared itself is not good because it should be the tensor of the fourth. It should contain 4 spin 4. It has spin 4. Spin is how under rotation this thing is in real space, how it transforms under rotation. And it has 4 minuses in the subscript. So we need something which has dimension q squared and has 4 minuses. The only answer is, only possibility is q minus to the cube divided by q plus. There's nothing else which you can write down with these properties. So we have the gravitational action, which is q minus to the cube divided by q plus, h plus plus, h plus plus. This is something which is it's W, it's the induced action actually. And there is no Einstein term. Normally we would add to the, like in QED, we have the Maxwell term plus polarization term. Here we have only polarization term. And it is very easy now to find the correlation function of H, which is simply the inverse of this thing. So we have q plus divided by q minus to the cube. And now we are ready to calculate the first correction. All this is enough to calculate the first gravitational correction to anomalous dimensions. We will do it. That's all very easy. What is less obvious is how to go beyond. Well, maybe before we start calculate, we have to clarify what really happened.
Yeah, why
Yes. Fair question, yes. And it's quite important. Well, it's much more straightforward and simple than that. So we expect in general that the induced action would be something like f of q squared. What it can be is delta alpha beta, delta gamma delta perpendicular in 2 dimensions. That's what we can expect. That's what we can expect because the other we just saw before that there's only one non-trivial combination in deltas in 2 dimensions. Delta perpendicular with other indices is equal to this index, to this combination of indices. Okay. All right. Now this time we multiply it. We say on dimensional ground we get q squared for this guy, and so it is q squared delta alpha beta delta gamma delta. And in the light cone gauge, what we get now we specify the light-cone gauge, and we get the W proportional to Q square. Here we will have Q minus to the fourth, and here we will have Q to the fourth. Am I clear here? Do you see what I'm doing? I have to multiply it by H alpha beta, H gamma delta. And then I take H to have only plus plus components. When I do this, I get the only term which contributes from here is the term which delta minus minus, which is Q minus square divided by Q square. And I take the square of this term. So we see that we confirm that this formula is equivalent to this one. So we confirm that in the light-cone gauge we got the correct answer. But what about the conformal gauge? So in other words, I'm saying that polarization operator is given by this formula, and we reconstructed it by looking at the light-cone gauge. Now, and this action is non-local. By the way, why it is non-local? So why we obtained the non-local? Why it is not surprising that we obtained the non-local action, having singularity at Q equals 0?
Because there was no compensating term. Like, I mean, here we had to subtract the term which cancels the singularity.
Well, right, but you see, here the singularity was, in the generic case, singularity was not allowed because we had massive fields. And so it's not our choice. We have no choice here. We must take the action which has no Q equals 0 singularity. In the case we are considering now, it is different because we have massless field. It is this massless field which created this singularity. Okay? And last, we are running a bit late, but to finish with it, and we will probably discuss a little more tomorrow. When you go to the conformal gauge, you don't get 0. But you get, in the conformal gauge, you have this conformal factor. If rho is e to the phi, the conformal factor, phi of q, q square, phi of minus q. We get non-zero. And this is the local expression. We get a local contribution. The meaning of it, which to be discussed in more details, but I will tell you the answer now. We will clarify it tomorrow. The point is that there are lattice or massive particle contributions not written here. Some what is called Pauli-Villars regulators, which are infinitely heavy, and they contribute to the action. But since they are infinitely heavy, they can only contribute the local expression. This is what is called the anomaly, quantum anomaly. We will discuss it next time in more details. But we're almost finished with it. There are 5 minutes probably of discussion still needed. Okay, let's stop here.